Chapter 4, Exercise 11. Use the definitions of uniform continuity and Cauchy sequences. Solution. Let f here be a uniformly continuous function between metric spaces this and that. Let xn be a Cauchy sequence in X and let epsilon greater than 0 be arbitrary. Since f is uniformly continuous, there exists delta greater than 0 such that this whenever that. Since xn is a Cauchy sequence in X, there exists an integer n greater than or equal to 1 such that this for nm greater than or equal to n, definition 3.8. Therefore, for nm greater than or equal to n, we have this. It follows that f of xn is a Cauchy sequence in Y. We now give an alternate proof of the theorem stated in exercise 13. Let E be a dense subset of metric space X, and let f be a uniformly continuous real function defined on E. We will prove that f has a continuous extension from X to R. Consider a point x and x. By definition of a dense set, definition 218j, either x is an E or x is a limit point of E. In any case, there exists a sequence xn in E such that limit n to infinity xn equals x. See theorem 3.2. By theorem 3.11, xn is a Cauchy sequence in X. It follows that f of xn is a Cauchy sequence in R. Theorem 3.11 implies that there exists a limit n to infinity f of xn, which we denote g of x. Note that the value g of x is independent from the choice of a sequence xn in E that converges to x. Indeed, if xn prime is another sequence in E that converges to x, then this. Denote y equals limit n to infinity f of xn prime. For any epsilon greater than 0, there exists delta greater than 0 such that this whenever that. For large enough indices n, we have the following. The choice of delta implies this and that. Since epsilon greater than 0 is arbitrary, we deduce that y equals g of x. Conclusion. For each point x in X, there exists a point g of x in R, which is the limit of any sequence f of xn, where xn is a sequence in E that is convergent to x. In such a way, we obtain a function g here. We note that functions f and g coincide on the set E. Indeed, let x and E. Consider a sequence xn equals x, n greater than or equal to 1. Since limit n to infinity xn equals x, we deduce g of x equals limit n to infinity f of xn equals f of x. The function g here is an extension of f. It remains to prove that the function g is continuous. Let epsilon be greater than 0. There exists delta greater than 0 such that this whenever xy in E with this. Assume that xy in X are such that this. There are sequences xn, yn in E such that the following. There exists an integer n greater than or equal to 1 such that for all n greater than or equal to n, we have this. Triangle inequality implies this. The choice of delta implies this. Since this, we deduce absolute value gx minus gy less than or equal to epsilon. Otherwise, we would have absolute value f of xn minus f of yn greater than epsilon for large enough n. We have proved that this implies absolute value g of x minus g of y less than or equal to epsilon. The function g is a uniformly continuous extension of f. Comments. In contrast with uniformly continuous functions, an application of a continuous function to a Cauchy sequence may produce a sequence which is not a Cauchy sequence. For example, consider the set here. With the usual distance and a continuous function f here, f of x equals 1 over x. The sequence xn equals 1 over n greater than or equal to 1, is a Cauchy sequence in X. However, the sequence f of xn equals n greater than or equal to 1, is not a Cauchy sequence in R. Thanks for watching.